Lesson 8, Part 1, the Intermediate Value Theorem. We have already discussed in class the proof of the intermediate value theorem. So now we're just going to use what are the big ideas. So one thing I want to point out before we start, though, is that this is an existence theorem. An existence theorem tells you that we know something happens, something exists, but we can't precisely say what that value is. So the importance of existence theorems is it lets us draw conclusions about behavior, which is very important, okay? Even if we can't say exactly what that value is, as I've said. So let's talk about what the big ideas are of the intermediate value theorem. So first thing we have to know is that the IVT, as it's called, has to work with a continuous function. That's important. So the idea of if-then, if this happens, then something else is guaranteed. And that's the whole crux of the IVT. So if a function f of x is continuous on a closed interval, then f of x takes on every value between f of a and f of b on that interval. So for instance, what this is saying is if f of a is 2 and f of b is 17, then f of x can have any value and every value in between 2 and 17 because it's continuous. There aren't any breaks, there aren't any jumps, there are no skips. So the IVT guarantees that if you're looking for an x that has a y value of 7.8, yes, it's there. So that's the whole idea behind the IVT. Even if we don't know exactly how to get that x, we know it does happen. Okay, another way to say this is that if we know a y value, what we've been calling a k, that resides between two endpoints, then there's at least one x value between the endpoints that generates that y value, such that f of c is k. And that's just what I was explaining with the f of a equal 2 and the f of b equals 17. Okay, so let's represent this graphically. So here's what we have. We have two different situations that we talked about. So let's say we have an A here, whoops, and B is here. We have a point right there, and then let's say B is down here. So we can draw our curve kind of like this. Okay, doesn't matter, just so it's a continuous curve. And let's locate C like right here. Let's call this C. So we have a point on the curve right up here. So let's label everything. So this way then, we're looking this way. At this point, we have f of a. And at this point, we have f of b. In the middle here, right here, somewhere in between f of a and f of b, this is our line, y equals k. Okay, so in this situation, we have that a is less than c, which is less than b, so f of b is less than k, which is less than f of a. Okay, so in this case, f of a is a larger y value than f of b. Now, it could be the other way, and it could be such that let's mark a line where a is and a line where b is. So this time, let's put our point at A here and our point at B up here somewhere. So let's say our curve looks like that this time. Okay, so here is our f of a, And here is our f of b. And I am going to call the point where the graph crosses the x-axis, that's going to be where x equals c is. And so that point is, that looks too much like a C. Oops. That point is C, comma, 0 right there, because it's on the x-axis. So what we have is that we have a situation where f of a is less than 0 and f of b is greater than 0. Okay, so f of a is less than 0, which is less than f of b. So this is a very common use of the IVT. So it can help us find zeros. It can help us find zeros on a continuous function. Because if we know one of the endpoints is a negative number and the other endpoint is a positive number, and remember, one of the conditions for the IVT is that we have a continuous function. So f has to take every value between that negative number and that positive number. So one of the numbers that's between negative and positive numbers is 0. So we can say that we have a 0. Okay, so that's kind of the background of that. So how do we use it in a problem? So we are to, I do not know why that keeps coming up. We are to decide if the intermediate value theorem can be applied on a specific interval for the piecewise function shown, and be sure to explain, and the important word there is completely. We have to be very precise in how we explain this. So our first job, looking at number A, is there a value of x equals c on the interval negative 2 to 5 such that f of c equals 1? So we're just looking from negative 2 to 5, okay? So what we can say is that, yes, looking at the graph, there is a value. So we can say yes. And I'll mark it on the graph. So we're looking for a value where f of c is 1. So right here, here's 1. It's right there on the graph. There's f of c equals 1. Okay? So yes, f of c equals 1 exists on our interval. Okay? All right, so the next question, this is the important one. Does the IVT guarantee a value of c on the interval negative 2 to 5 such that f of c equals 1? Justify. So the answer to that is going to be no, even though it is there, because the IVT does not guarantee a value of x equals c on the interval. This is how precise you have to be. Since f of x is not continuous on that interval. Now, it could be continuous on a different interval. If we were to pick the interval, say, 2 to 5, positive 2 to 5, then we could say yes, because that part is continuous. But if we're looking from negative 2 to 5, we cannot use the IVT. Even if we can look at the graph and see the value exists, you cannot use the IVT for that. Doesn't guarantee it. Okay, so next question is there a value x equals c on the interval 1 to 6 such that g of c equals 3? Okay, so again, we're looking at 1 to 6. And so if we look 1 to 6, what we see is that Here's 3. There is no value there. There is no value there. So the answer is going to be no. There is no value where g of c equals 3 on that interval. Okay, does the IVT guarantee that a value of c on the interval 1 to 6 such that g of c equals 3? And again, no, it does not. And here's why. It's a little different because that does look continuous there. The IVT will not guarantee a value where x equals c on the interval, since f of 1, which is the first value, should be less than g of c, should be less than f of 6, or vice versa. Depending on which direction the function is headed. So it doesn't have to be low to high. So if g of c equals 3. Because if you look at your values, the highest value you have is f of 1, and f of 1 is like 1.5 here. And our lowest value is at 6, and f of 6 is -1. So you can't have 3 because 3 isn't between 1 and -1. Okay, so the 3 conditions that are necessary, they are f is continuous, which we did not have in the first problem, the first graph. The second one is that the endpoints cannot be equal to each other, or you can't have any values in between them. So f of a cannot equal f of b. And the third value, the third condition, is f of c has to be between f of a and f of b. And that's what broke down in the graph of g that we just did. Okay, so that's trying to give you kind of a visual representation of this. Okay, so now what we're supposed to do is apply the IVT, if possible, on 0 to 5, so that f of c equals 1 for the function f of x equals x squared plus x minus 1. So here's how you need to start all these if you're using the IVT. First, you have to state that f is continuous if it is, or if it's not, you need to state that. So we can say that first, that f of x is a polynomial so f is continuous on our interval, because polynomials are continuous everywhere. Okay, so next we want to check our endpoints. So f of 0, when we put 0 in, we get -1. And f of 5, when we put 5 in, we get 29. And the reason we do that is we want to see if the value they're looking for, which is 1, is that between our two endpoint values. And in this case, it is. So we say, by the IVT, there exists a value c where f of c equals 1, since f of 0 is less than f of c, which is less than f of 5, and C has to be between 0 and 5. Okay? And if you want to be a little more specific here, you can also add your f of 0 values. So like that. So that's what they're looking for. Okay. So next example. So we're going to use the IVT to show that f of x equals x to the third plus 2x minus 1 has a 0 in the interval 0 to 1. Okay, so the first thing we want to start with is to talk about whether or not we can use the IVT. So f of x is a polynomial again. Therefore, f is continuous on 0 to 1, because we have a cubic function here. Next, to finish, to make sure that we can use the IVT, remember our three conditions that we wrote at the bottom of the first page. F of 0 is going to equal -1, and f of 1 is going to equal 1. And so we can see then that the endpoints are not equal to each other. So that's good. So, is there a 0? What we can say then is since f of 0 is less than 0 and f of 1 is greater than 0, there exists a value x equals c on the interval such that f of c equals 0 by the IVT. And you can write IVT. Everyone in math knows what the IVT is. So that's how you show there's a 0. We showed the conditions were met, and then we can say that C is between the two endpoints, and since one endpoint has a negative value and the other is a positive, we can say that the IVT exists. Okay. So let me stop this video here, and then I am going to finish it in part 2.